What's going on, guys? My name is Zayotic, and I'm here with another VulnHub CTF. This time it's Brainpan, and this one has a lot of buffer overflow, Windows and Linux buffer overflow exploitation. So that's what we're going to be doing in this video. I already got the IP, and I have a Windows 7 virtual machine set up so I can diagnose the executable that I'm given. I basically got it from, let's see, basically I did a, this is the Nmap scan. You see there's a web server and there's a service running on 9999, and this service, you can actually connect to it. With the netcat at that port, and you can see you get this. The objective of this is not to get the password, although if you do want to get the password, you can get the binary from the /bin directory, and yeah, it should be here, and it's shitstorm. So that's not really the objective of this, but that's basically how you would get it if you wanted to get it real quick. I have a series of scripts here already set up just to save time. But basically I'm going to go over each step that you take. So yeah, basically go over to the Windows machine. I was playing with it earlier. Just ignore all this. So yeah, I'm going to run the executable. Going to attach it and start it. So yeah, we're basically going to be fuzzing it to see exactly of how much data the crash occurs, and you want to make sure this is the script I'm using. It's basically just doing a for loop, and it's yeah, just sending a bunch of data over a socket connection, just sending a bunch of A's. So it's really all it's doing. So I'm gonna run it. Stops at 900 bytes. We want to write that down. So that's when the crash happens. We write that down because we want to account it for our offset later in the Python script, which I'll show here. So now that we know it crashed at 9,000, go ahead and look at it, and we see the EIP has successfully been overwritten. And we can get a better look at the crash. See, it's just a bunch of A's, and yeah. So now we're actually going to try to get control of this EIP register. That way we can redirect execution to a specific address that we're looking for, so we can redirect execution to our shellcode. So to get control of the EIP, you basically, I'm going to use a Metasploit tool called pattern create and pattern offset. This should be in this directory, and pattern create, and we're gonna have a length of 900 because that's what it crashed at. So take this and go to Brainpan exploit, and I already kind of have a template here. It's just creating a socket and connecting, and yeah, basically what matters is our buffer. Our buffer right now is just going to be that pattern, and that's all it's going to be sending. So we're going to go over to the 7 machine and start the process back. There we go. So now that we have it running, we sent it, and I don't think it's crashed. Oh, I know why. It's because I sent it to the wrong IP. Yeah, I sent it to the Brainpan machine, which means I have to restart it because I crashed the process. So Yeah, I'm going to start it up that way the service starts back, because we're not ready to attack it yet. That's what we're doing this for, diagnosing the vulnerability. So yeah, basically we need this IP. Okay. Change that to a 3. Now it should work. And it crashed. So that's good. That's what we wanted. And you can see our EIP landed on a different address than just A. This is a part of our pattern. This is a pattern that never repeats itself. So that's how we can kind of figure out the exact offset that the EIP is at, so we can override it. So that's a very important instruction. So, or very important number you want to write down. So, because you want to put this, you want to give this number to the pattern offset tool with containing the metasploit. So replace it with what it landed on, and replace this with offset. Oh, it did. And there we go. Our exact offset is 524. So write that down. Okay. So now that we have that, let's go back to our exploit. Let's repeat a bunch of A's at 524, and then after that, let's do B's, and this time 4 bytes. And we still, remember, we still want to recreate the crash, so we're going to create a bunch of C's and times this with 900. That way we can recreate the crash, so we can examine this. Then we want to subtract it by 524 and 4. So we want to account, we want our offset to account for what we're putting in. So that's why we do that. We let Python do the math for us. So before we run it, we gotta make sure everything is set up. No longer need that. So I'm gonna run attach. Okay. So now we can run the exploit. And there we go, it successfully worked. We now have control of the EIP. We know this because this is B's instead of A's. We can, let's go ahead and look what's going on. You see, that's where our EIP is pointing to, and this is our entire stack. And this is basically how much space we're going to have for our shellcode. So, yeah, now that we got control of the EIP, we want to check for bad characters. Just so, so we don't have any characters in the shellcode that could disrupt the execution. So that's why we do this. No, not fuzz. I meant to open up see, I already have this here. I took out a few which I knew would be bad characters. This is more of an example. See, we do the same here. We recreate the crash. We implement bad characters. Then we account for that in our offset. Let Python handle all of that. Looks like the IP is correct, so I don't have to worry about that. So let's go and run. Do the same routine. And we'll run the script. We want to dump the ESP register. And you can see that our buffer, our bad characters start here. So you can see it's counting. So yeah, it doesn't, you know, it usually show here, but it doesn't look like we have any bad characters. So except two, which I'm going to, which is hex 00 and hex 0A. And we're going to take that into account when we generate our shellcode to make sure we don't have those bad characters. So now that we got bad characters out of the way, next we're going to actually exploit the service. We're going to exploit our virtualized, like our Brainpan on VM. This we're going to exploit this Brainpan, and then we're going to exploit this one. So we figured out that we can, and then we're going to actually do it to the other one. But first we need to actually figure out something to replace the EIP with. And to do this, let's go back to Windows 7, and we're going to use Mona to help us. And if you don't know what Mona is, all you have to do is install it from GitHub, the .py, and put it into the py commands folder of Unity Debugger. So I'm going to run Mona modules. And we can see the brainpan.exe does not have ASLR or anything that we need to worry about, so that's good. So next we're actually going to search for a certain instruction among the Brainpan exe, so we can actually jump to that instruction and you know, preferably a jump ESP. And how we actually get the opcode to figure this out is we can use Metasploit's NAS and shell tool, and we can write like a ASM instruction like jump ESP. Like this is what we would want to replace our EIP with, and it would give us FE4. And we're going to take this bytecode and we're going to put it in little endian format. So now that we have that, we can write that down. That's the opcode of the instruction we're looking for. We're going to go back to our crash, and we're going to use Mona to find what we're looking for, that specific opcode. So remember, we're going to do little endian, and it's E4 and brainpan.exe, and it found this specific instruction, so we want to write that down. So let's go back. Let's go back to our exploit. I'm going to go ahead and paste this here as a comment. No, that is the address. So we need to convert this to little endian format. And 31. So that should be it. It's backwards when it's in little endian, so that's going to be 4 bytes. So yeah, we basically just want to see if it actually jumps to that instruction. So we have it written down so we can find it if we need to. Let's attach it. And I'm looking for a certain instruction. Yeah, sometimes you have to do it twice. There we go. That's the instruction we want to jump to. I'm going to set a breakpoint right there, just so we can make sure it actually goes to that instruction. So I'm going to it hit our breakpoint, so we successfully jumped to this instruction. See, the IP is there, so see where it goes. It goes back to the ESP, the stack pointer, where there is nothing. So successfully did that, so we're on the right track. We're going to be actually setting up our shellcode, and I'm just going to use a reverse TCP shellcode generated using MSF Venom. So that would be, and we are doing a Windows payload. That's because this exe is actually running in a wine environment, which, you know, is a Windows compatibility layer. So this shellcode should or will still execute. Make sure I have the IP correctly. This is connecting back to me. So I'm going to need to change this when I'm going to need to regenerate this shellcode because when I actually do it on the Brainpan VM, it's on a different interface. So I need to account for that, or else it won't work properly. The socket, the reverse TCP connection. Okay, it turns out that I spelt the encoder wrong. So that's why it wasn't working, because the payload wasn't even encoded. So I'm going to take the correct shellcode, put it into our exploit. I'm going to go over here. And I'm going to set a breakpoint. And it hit the breakpoint. I'm going to use F8 to continue. Here's our NOP slide. And then it's going into our shellcode, and now it's decoding. So we can see our shellcode develop in real time. I'm going to go ahead and set up a netcat listener. And there we go, get our shell. Okay, so that is how you conduct Windows privilege or buffer overflow for Brainpan. So we're going to see. Well, oh, I forgot. Yeah. Now that we know it works, we're going to try it on the actual CTF itself. Now that we've diagnosed the vulnerability and we've basically played around with it. So we're going to take this exploit that I used, and we're going to connect to the Brainpan machine. I'm going to set up a netcat listener, and there we go, it worked. So that's how you get you exploit Brainpan, at least Windows exploitation. So you can see we have a shell. Let's see what this is. So you can okay, this is a script that it was running on reboot to it's using wine to run brainpan.exe, and we just exploited that and got a shell. We could set up a simple HTTP server to install a binary. Name it fun.bin, just so it has different naming. Yeah, the shell is kind of weird now. There, I did it that time. Okay. There we go, it worked. I was waiting for it, I didn't know if it would work or not. So yeah, we got a Linux shell now. Let me go and try to get me bash. There. So now we can close this shell. Okay, now we have puke. We have a Linux shell. Okay. So we can see that we have 3 users. Let's see what permissions we have. We can see that there's a file owned by, let's get a look at that. They won't let me see it. So let's see if we can find any other files owned on this by this user. And just going to search the system. There we go. So we do see that this this user does have permissions to this binary. So just see that it's completely owned by that user. So it looks like this is going to have a buffer overflow vulnerability. See, it takes an input. So yeah, now we're going to begin Linux exploit development. First, I'm going to actually get this binary so I can play with it. Try to copy that to the validate directory. Okay, it should be there. There it is, validate. So that's a way we can get the binary. I'll exit out of this. And now that we got the actual binary, let's go ahead and so I just want to have this, you know, to diagnose the binary and, you know, see, just test things out. I'm going to keep that open, obviously. Create a new window. So we have this validate binary, and if we can perform a buffer overflow and get a shell, we will be the permissions of the user that owns this file. So we could do add Python to this. Print A's 60 times. Passed. Passed. Okay, it crashes at 200. Ignore all this. It's irrelevant. Already been through that. So it crashes at, so that's kind of like fuzzing. Now I'm going to do is I'm going to use GDB to open the binary, and I'm using the extension PETA to assist me. And so the command is actually checksec. Okay, see, we don't have, all those are disabled, so we don't have to worry about that. I'm going to disassemble the binary, and I'm going to probably set a breakpoint to that address. Oh, I actually didn't mean to run. Yeah, it needs input, so we'll just do print. Actually, real quick, I'm gonna find the offset. So, real quick, let's go back to pattern create. Give it a length of 200. Okay, now run. Took in our inputs in the EAX register. Let's go to the next instruction, and it's going to be putting our our data in EAX into the stack pointer. And there we go, it's in the stack pointer now, and we can examine that it's actually slash. I don't know why. I'm just, I don't know, kind of tired, I guess. And that is pattern offset. So we're going to figure out serial stack is getting overwritten with it. We can see that our instruction pointer landed on this memory address. So I'm going to go ahead and write that down, and that's what we're going to, well, let's see if, yeah, just change this and put in our offset. An exact offset of 116. So now that we know that, back to GDB, and this time give it a bunch of A's and do times 106, which is what our offset was. And let's add that plus B's. Let's run, slowly run it, and it crashes. And it worked. We successfully overwritten the EIP register. We have found out the correct offset. And that's verification, because after the program crashes, we have control of the EIP. We did this all within Python. So now we actually want to, just like kind of like with Windows exploitation, we want to well, really what's different here is that we want to actually put our shell code into where these A's are, because that's what our buffer is going to be. I don't know why I keep getting confused by that. Oh, it's crashed, so it's not going to work. Of course, I don't. Okay. So next, we're actually going to, we're going to add on our C's. And we're going to do this by 200. Run that. Next instruction, next instruction. And it crashes. Actually, that's not what I wanted. I wanted to just do an examine on EAX, the main accumulator. See, those are our A's coming in. And that's where instruction pointer is pointing to. So it's a lot like last time. This is the so it looks like this is the actual space for our shellcode, which is fine because we're not going to be, our shellcode this time is not going to be utilizing sockets to do like a reverse TCP like the Windows one does. This one's just going to be directly give us a shell. So we really don't need that much space. So what we're going to do now is we're going to inject our shellcode into the buffer. So I'm going to open up this new window and generate quick shellcode. You could write this yourself, but I'm not going to because it's out of the scope of what I'm doing. So it's going to be an execute. And by the way, I've already identified bad characters. You would do that just like we did in Windows exploitation, but just to save time, I'm not going to do it because this is already going too long than expected. But these are the bad characters that I found in my analysis of this Linux binary. And series 46. Yeah, and these are the bad characters that I found in this binary, and I'm going to take account for that in my shellcode. So hex 00 0D 0A 20 46. Shit. Okay, there we go. And our encoding. Make sure to spell right. There we go. 70 bytes. Is the shellcode length. Take this and we're going to adjust it to fit our situation. Take all this and make it one string. And let's go back to GDB. And now that we have our set shellcode, we're actually going to figure out what we're going to replace the EIP with. I just wanted to go ahead and generate the shellcode, but we're going to figure out the EIP by searching through the binary for any instructions that we want to replace it with. And we're preferably looking for anything like jump ESP, jump EAX, or anything like that. So that's what we're going to be searching for. We're going to be using object dumped to figure this out, just to speed it up. And object dump will output it and use grep. We're going to search for a jump ESP first. No jump to ESPs. Jump EAX. And call EAX, and we get a call EAX in the binary. See, this is the bytecode for it. Okay, we're basically going to want this right here. So we're going to take that instruction and we're going to want our return address or EIP to point to that. to execute our shellcode. So open it with validate. We're going to move for about right there. Oh, it needs input. Yeah, I keep forgetting. But let's put our shellcode here. Did not want it to do 2 commas like that, but whatever. Take the shellcode. I'm going to create our NOP slide, kind of like what we did last time. So that'd be X 90. And we're going to do that by 1.6 to account for our offset like we did last time. And the length 70. Next is our what the EIP is going to point to, our return address. And we just want to convert this address to Little Indian. So AF and this will be 0A. So this is our return address. And run it. EAX is going to contain okay, it says is executing new program. Okay, so it looks like it worked. So let's take the command I used, that way I don't have to write it out again. But this command is basically our exploit for this binary. There we go, our shellcode. Then our NOP slide take into account our shellcode amount and our shellcode length. And then we're replacing the instruction pointer with a push EAX, because EAX is what's going to contain our shellcode. So yeah, let's test it out. I didn't mean to do that, but instead of GDB, we're just going to do validate. And it seems to want to do something weird when it gets pasted. Yeah, it's printing out really weird. I'm actually going to take this and put it all in one line. That must have been the issue. And there we go. We got a shell. And use Python spawn bash. Okay, so now we know it can be exploited. We're in our own machine, so it's kind of weird, but yeah, we know that this is our exploit. We can run it and it'll be all in one line. And yeah, let's go over. I'm going to go over to this user's bin. There we go. Got root. There we go. So all we had to do was replace the file owned by this user, which we saw with sudo. We have privileges to run, or you can't see it now, but earlier we did. And yeah, just copy bin, replace the file as bin/bash, and of course run it with sudo with root, and we have a root shell. So let's look at what he wants to tell us, and all it is that. So yeah, if you guys enjoyed this CTF, I'd really appreciate liking the video. Sorry this one was a little bit long, but it covers 2 in-depth exploitation methods, and I kind of wanted to go over it a bit fast, but also explain it the best I can. So yeah, if you guys enjoyed this video, appreciate liking, and goodbye.